Welcome to the FMSP revision sessions. We're looking at MEI FP3 groups, and we're going to start off by looking at some of the specification statements. These are things that you need to know to do your exam. So obviously the first thing we need to know what a group is, and we start off by saying, well, we've got a set of elements, G, and an associated operation, which is often has some kind of a star or something like that. And the operation tells you how to combine two elements of the group. To make it into a group, we've got 4 axioms. The first one is closure. And what closure is when you've got 2 elements of the group and you put the operation on them, you get another element. If that's in the group, that shows you've got closure. So that's what you have to check. There are 2 different sort of situations you might have. You might have a finite group, in which case you might be asked to draw a Cayley table. That's a 2-way table combining the elements of the group. Or an infinite group where you'll be given, say it might be all the integers, or it might be something like even numbers, positive integers, and then you have to combine 2 general elements and show that what you get when you combine the general elements will also be a member of the set of elements that you started with. So closure tells you when you combine 2 elements of the set, you get another element of the set. The second one is associativity. Now, associativity is the one that sometimes they'll tell you you can actually state. And what this says is that if you do A star B and then star C, that's equal to A star B star C. Often, as I say, you can assume this, particularly when you're looking at things, for example, multiplication modulo a certain number, combination of matrices. If you're multiplying matrices, they'll often tell you, or it'll be fairly obvious, that you can assume this. But sometimes, and particularly again for your infinite ones, you will need to take some 3 general elements, combine them in the way that you're told, and show that you get the same thing, combining them in the 2 different ways. The third thing is there must be an identity element, and this is usually pretty easy to spot. This is an element that leaves all other elements of the set the same. So EA, if A is your general element and E is your identity, equals AE equals the element A, where E is the identity element. Okay, so for example, for multiplication, 1 is an identity element, but don't always assume it's going to be 1. But that, again, you can see that from the table. If it's an infinite set, you will need to combine it and maybe use some algebra to get there. And the fourth one is that every element must have an inverse. And again, the way you spot that is that if you've got an inverse, if B is an inverse to A, then AB is equal to BA, and that's equal to your identity. So combining them in either order gives you identity. And for an infinite set, again, you'll have to take 2 general elements and use algebra, but you can just use one of these statements to find the inverse. There are lots of different kinds of examples of groups you might come across. Some common ones could be symmetries, modulo arithmetic, permutations and combinations. Permutations of sets of elements. Those are common ones that come up again and again. You might also be combining matrices or complex numbers and other elements that they might tell you, algebraic fractions, for example. The use of group tables, as I say, we need to put things in K-tables, but we'll get some practice at that when we look at the exam questions. A cyclic group is a group that can be generated by a single element, okay? And that's what it says here. A single element can generate a cyclic group. So that means if you take an element, A, and then you work out A squared, A cubed, up to the order of the group, and the order of the group is the size of the group, if that gives you all the elements, then that means you've got a cyclic group. And the interesting thing here is if you look at it, because you would want A to the n plus 1 to go back and give you A again, that means the A to the n must be equal to your identity element. But it may be that other powers, for other elements, maybe other powers will get there, but in this case, you're not going to get to the identity element until you get to A to the n. It's worth looking and thinking about cyclic groups when we think about some of the theorems later on, Lagrange's theorem particularly, and that's when we say that the order of an element or the order of a subgroup has to divide into the order of a group. And what this means, and I'll mention this again later on, is that any group of prime order must be cyclic. And I'll mention that later on, but this comes from the fact that if this is the first element to get to the identity element, that means that's the order of this element. Well, the order must divide that, but prime numbers only have divisors of 1 and themselves. So that means that an element must generate the group unless it's the identity element. So prime groups must be cyclic. And that's quite a useful thing to know. The order of a group I just mentioned is the size of the group, and the order of an element, as I said, is the power which you have to raise that element to get the identity. So it's the smallest value of n such that a to the n is equal to the identity element. And you can check that with a finite group simply by doing the powers of them and seeing when you get to the identity. And we'll have a look at doing that at tables and how you can sort of make that a little bit faster. A subgroup is some elements of the actual group, and it could include the group itself, such that they form a group in their own right. Okay, so that if you've got a subgroup of the actual set of elements of a group, in them you must have the identity. If you've got any element, you must also have its inverse, and you must have the other things. You're obviously going to have closure. To make it a group, if the main group's associative, then any subgroup will also be associative because that'll just fit the laws. So you just need to check that you've got the elements and their inverses. Lagrange's theorem helps you find the subgroups because Lagrange's theorem says the order of an element must be a factor of the order of the group. And obviously, because of that, then the order of a subgroup, if you think about it, the order of a subgroup must also be a factor of the order of the group, because any elements in it must have an order that's a factor of that. Okay, so when we're looking at a group, say, of size 8, then any subgroups could have 1, 2, 4 and 8. And so when you're talking about subgroups, you should always include, if they say all subgroups, the one that has all the elements in it, which would be the full group. And in addition to that, the identity element will be a subgroup in its own right. And then there may be other ones. It's worth mentioning here that any subgroups of order 2, they must always have the identity element. They must have one other element. And so that element must be self-inversing. So it's a very easy way of finding those subgroups of order 2 if you look for the self-inversing elements. Subgroups of order 4 are also worth mentioning because there are just 2 kinds. The cyclic group of order 4, and then there's the Klein group of order 4, which has got 3 self-inversing elements and the identity. And you may be asked to prove that. And if you go through what the possibilities are, it's quite easy to show that there can only be 2 groups of order 4. So that's sort of something common that might occur. Different situations that can give rise to essentially the same structure, and this is sort of similar to what we're talking here. If you get 2 groups where you get the same structure, then those groups are isomorphic, and that means there's a one-to-one correspondence between the elements. And sometimes it's easier to see why that would be than other times. But for example, if you think about rotations, you can also think about that being related to complex numbers or multiplication. And so sometimes it's quite obvious why you would get a correspondence, and sometimes it isn't, but you can still get a correspondence. So for example, if you've got a group that has a prime number, and we mentioned that before, and this comes into Lagrange's theorem, that if the order of an element has to be in order of the group, if you've got a prime number, for example 7, then that means the order of the elements must be 1 or 7. The only way you can have order 1 is if you're the identity element, so all the other elements must have order 7. They must generate that group, so you get a cyclic group. So any two groups of order 7 are going to be cyclic. One element will generate them. If you look at the powers of that element and put them together, that will give you a one-to-one correspondence between the groups, so they must be isomorphic. Okay, so what we're going to look at now is look at a couple of exam questions. We're going to look at June 2010 and June 2011, go through the exam questions, have a look at how to do them and how the mark schemes work. Okay, so we start off by this one. We've got a finite group. It's a situation that's slightly more unusual. It's algebraic fractions, but not particularly tricky. And we're looking at composition of functions. So we've got these fractions which are giving us functions. And nice easy question to start with. Show that ST equals R and find TS. And that'll help us start to fill in this table. But in addition to that, it'll tell us, make sure that we're confident about which way around this table works, which is going to be important in a bit. So ST, if I look at ST, you just need to remember that ST of X means you put T into S. So you do T first and put that into S. So wherever we got X in S, we put X over X minus 1. So that's X over X minus 1 over X over X minus 1. And obviously if you multiply the top and bottom by X minus 1, we get X minus 1 over X, which gives me 1 over X. And hopefully when I look, I get 1 over X is R. So I've shown that's the case. Okay, so I've shown that ST equals R. And if you look in the table, they've already put that element in here, ST equals R. So you know that in the order ST, it goes in this order, just in case you weren't sure. We have to find TS, and this is going to be interesting because it's going to show us whether the group is commutative or abelian or not. And abelian, we didn't mention that before. A lot of people think this is one of the group axioms, and it's not. Abelian is when, for all members of the group, A star B is B star A. And it's not one of the axioms, but it's a common feature of groups, and it's quite an important one to know about because sometimes this can, for example, disprove that you've got isomorphic groups. If one is abelian and one isn't, they can't be isomorphic. So that's something to bear in mind. So anyway, let's look at TS. So now we're starting with S and putting that into T. So we're going to get X minus 1 over X over X minus 1 over X minus 1. So multiply it by X, we get X minus 1 over X minus 1 minus X. And that's going to give us a minus 1 on the bottom. So that's going to change the top into 1 minus X, which is Q. So TS is Q. We can put that into our table. Now we've got a couple of things that we can do here if we want to. We can use the fact of closure, and one of the effects of that is that every row and every column has each element in it, a bit like Sudoku, and we could use that to have a look at what must be left in here. So I can see that I think US is going to be equal to P, but obviously if you want to check that, it is worth doing that and checking what we get with US, but you can use that fact to help you find that if you want to. So let's put S into U. So that's 1 over 1 minus X minus 1 over X. That gives me X over X minus 1, which obviously gives me X over 1, which is X, which is the identity element P. Okay, so that one did work. T squared, I'll put T into T, X over X minus 1 over X over X minus 1 minus 1. Gets a little bit tedious this, but it's not very difficult. Okay, and if I work this one out, I'm going to get P as well. And again, what I'm going to do, just to save us a little bit of time, because I think combining them is fairly straightforward, I would recommend double checking them, but we can have a look again and we can see that in the T row, that we haven't got on R, and in the T column we now haven't got a Q, and the U row and column we haven't got an S. But it may be worth just double checking one of those to make sure that you haven't made a mistake. But you can use that fact that every row and column has each element in it once, only once, to fill the rest of that table in, particularly if you're a bit short of time. So I've put that table up here for us to refer to, and we're going to look at part 3 of this, and we're going to look at the inverse of each element. Okay, so let's have a look. We've got all the elements. We've got P, Q, R, S, T and U, and we need to look at the inverse. Now, obviously, P times P combined with P gives me P. Okay, if I look at Q, I need to get the P, so that means Q is self-inversing as well. If I look at R, I need to think about what combines with R to give me P, which is the identity. So R is self-inversing. If I look at S, it's U. Okay, and that should mean that U is S, but we'll check that in a minute. If I look at T, it's T. And if I look at U, it's S. And that should happen both orders. So obviously that's why U and S and U give me that. So that's the inverses of them. And that can help me to find the subgroups. So if I look at all the subgroups of F, well, actually, in this case, they didn't worry too much about these ones, but we should always include, if they say all the subgroups, the identity and the full group. But in this case, they didn't actually take any marks off if you didn't get those, because the ones they're interested in are the other ones. Now, because it's a group of order 6, it could have subgroups of order 2 and 3 as well. And 2, we said, are the self-inversing ones, so P and Q, and P and R, and P and T. And that conveniently leaves us with P and U and S. And U and S are self-inversing, so U times S is P and S times U is P, so that is going to give us a subgroup of order 3. Okay, and there can't be any of other order. We haven't got any other elements to put into another subgroup of order 3, so we can be fairly confident that we've got all the subgroups there. And here's the mark scheme for that, so you can see the way that it was marked. For 3 marks, 2 for 4 correct, 1 for 2 correct, so you basically 2 marks for each of those. And for part 4, as you can see in this case, they just gave you 1 for each subgroup, but that's not always the case. They might sometimes knock off marks if you didn't get the identity and the full group. That does depend on the paper. So now we've gone to the rest of the question, and they're adding in a different kind of group for us to have a look at. We've got a group here with multiplication of complex numbers as its binary element. Find the order of each element of M. I'm going to just write them underneath for simplicity, so I'm not having to do too much writing. Obviously, when we think about it, it should be fairly obvious that we're looking at multiplication, and so 1 is the identity element, and so that has order 1. Okay? Minus 1, well, if you do minus 1 times minus 1, you get 1, so that's going to have order 2. And then we get the other ones that are a bit trickier. We know the order of these elements can only be 1, 2, 3 or 6 from Lagrange's, but we need to think about how do we get to 1, and if we write 1 as equal to e to the 2 pi I, 2 pi j in this case, 2 pi j, that's going to make life a little bit easier for us, because that's going to tell us that to get to e to the 2 pi j, we need to take this to the power 6. Okay, there's no element before that where you're going to get 1. You're going to get minus 1 if you do it to the power 3, because that'll lead to the pi j, which is cos of pi plus j sine of pi, and cos of pi is equal to minus 1. So we have to do that to the power 6. And equally with this one, if we do it to the power 6, we're going to get e to the minus 2 pi j, but you should be confident that's the same thing. This one here, though, we just need to do it to the power 3, and this one to the power 3. Okay, so we've got the order of each element using what we know about complex numbers multiplication. And then we've got another group here, but somehow these two are going to come together in a minute. The group G consists of positive integers between 1 and 18 under multiplication modulo 19. Show that G is a cyclic group which can be generated by the element 2. And I think this is quite hard to know exactly what they want, but the key is the cyclic bit. They just want you to show that 2 generates it. So 2 to the 1 equals 2, 2 squared equals 4, 2 cubed equals 8, 2 to the power 4 equals 16. We're still not being affected by this modulo bit, but then 2 to the power 5 is 16 times 2 is 32, which is, I'm going to write that in brackets, equals 32. If we take 19 off that, we're left with 13. So 13 modulo 19. So 2 to the power 6, rather than going back to the 32, if we just go back to the 13 and multiply that by 2, we get 26, which is 7 modulo 19. 2 to the power 7, 2 times 7 is 14. 2 to the power 8, again we can multiply that by 2 and get 28. Modulo 19, that's just equal to 9. 2 to the power 9 is equal to 18. 2 to the power 10. If we multiply 18 by 2, we get 36, which is 17 modulo 19. 2 to the power 11, etc, etc, etc. I'm going to just write the rest of these down because I think you can do the multiplication in your head. So there's quite a lot of these to work out, and this is all they wanted you to do to show it generates the group. Okay, they're not asking you to, this will show closure because you get all the elements of the group. You've shown you generate it. You know that you've got associativity because it's multiplication. It's pretty obvious what the identity is. And so this is what they're asking to do. So you've got 2 has got order 18. It's the first time that you get to this identity element, and therefore it generates the group. Okay, in case you couldn't read any of those, I've got the mark scheme here, which shows you how you get the marks. So finding at least 2 powers, you get 1 mark. There are 2 specific ones they want you to get to 2 to the power 6 and 2 to the power 18, and that's going to be relevant in a minute, and you get your order 18. Okay, we might come back to that table in a minute because we need to think of subgroups of that in a minute. So the first thing is explain why G has no subgroup that is isomorphic to F. Okay, now let's have a think. We haven't got F here, but G that's F. That was our F, which had our 6 elements, and there must be some simple reason why G, with these 18 elements here, can't have a subgroup that's isomorphic to it. It can have a subgroup of order 6, but why can't it be isomorphic to F? And it's 1 mark, so it's obviously going to be a simple reason, and in this case, a simple reason is probably the most obvious one, is the fact that F is not abelian, it's not commutative, the elements aren't commutative, and that G is abelian. Okay, so in that case, it's fairly obvious that you can't have that subgroup. You could also look at the order of the elements, and it turns out that you can have subgroups of, for example, F isn't cyclic, but abelian's the main one that they're probably looking for here. But we need to then find a subgroup of G which is isomorphic to M. So we want something where we've got an order 6 subgroup, a subgroup of order 6. And the obvious one to think about here is to think, well, how can I get something of order 6? If it's got order 6, so I'm going to go back to these elements here, that means that I need to get to 1, but instead of 18, I want to the power 6, something to the power 6. Well, if I think about that, that's 2 to the power 3 to the power 6 is equal to 1. So if I take the elements 2 to the power 3 and multiply them, 2 to the power 6, 2 to the power 9, 2 to the power 12, 2 to the power 15, and 2 to the power 18, that's given me a subgroup of order 6. And thinking about what we get here, if we think about this element of order 6 that generates it, you multiply it, you get that one, etc., etc., that should give you an isomorphism. Okay, and in fact, that's the obvious way of getting a subgroup of order 6, and that is the answer. So your elements are U1, 2 to the power 3, 2 to the power 6, 2 to the power 9, 2 to the power 12, 2 to the power 15, which give you the elements 1, 7, 8, 11, 12, and 18. Okay. And again, there's the mark scheme for that. I don't think there's anything particular to say about the mark scheme there. So that's 2010. So we're going to now look at June 2011. Again, question 4. That's what group questions are always question 4 on the paper. And we need to show here that we've got our set G, and that's going to give us a group. So the way to do this is to start off by looking at the Cayley table, 1, 3, 4, 5, 9. Okay, and this is what's going to show us the closure. So it's modulo 11, 1's obviously multiplies everything and gives you that, and that also tells me that we've got an identity element. So I'll write that down while I remember. So 1 is the identity element. Okay, 3 times 3 is 9, 3 times 4 is 12, modulo 11 that's 1, 3 times 5 is 15, modulo 11 that's 4, and 3 times 9 is 27, so that's 22 plus 5. Okay, 4 times 3, so we get 1 again, 5, 9, 3, and again I'm sure you can multiply these out relatively easily, modulo 11. And you do get this table, so this table shows closure. So we need to mention that table shows closure. They've said we can assume associativity because it's multiplication. We've got an identity element of 1, so we just need to then find the inverse. So we've got 1, 3, 4, 5, 9. Inverse of 1, obviously the identity is 1. Go down 3, the inverse of 3 is 4. The inverse of 4 is 3. The inverse of 5 is 9, and the inverse of 9 is 5. Okay. Explain why any two groups of order 5 must be isomorphic to each other. Well, we did mention that in the statements at the beginning, that 5, the key to this is that 5 is prime. So it must be cyclic. And two cyclic groups of the same order must be isomorphic. And it's enough to say that. Isomorphic. Okay, it's enough to say that. You might also say that, you know, you can do a one-to-one correspondence of the generating elements and their powers, and that gives you a way of finding the isomorphism, but it is enough to say that in this case. Okay, so here are the mark scheme for that. 2 for the table, 1 for saying it shows closure, 1 for saying what the identity is, and 2 for the inverses. And again, what I said here is that you say that 5 is prime, group of order 5 must be cyclic, and two groups of the same order must be isomorphic. So those are the two cyclic groups of the same order must be isomorphic, and those are the things that you need to say. Okay. We've then got, I've left that group up there because we might need to come back to that. We've now got the set H, which is a group under binary operation of complex numbers again. And we need to specify an isomorphism between G and H. Okay, so obviously the identity elements must go to each other. And because it's a cyclic group, what we can think of is that any element can generate the group. So let's use this element to generate this group, because if you square it, you get the next element, square it again, square it again. So so you multiply it by itself again, multiply it by itself again. Sorry, not square it, multiply it by itself. And so we'll use 3 to generate this group just for ease. You could start with any element here. 3 squared gives you 9. 9 times 3 gives you 27, which we knew was 5. And 3 times 5 gives you the 15, which gives me 4. Okay, so what I've done is I've just gone through 3 squared, 3 cubed, and 3 to the power 4. And in the same way here, that's e to the 2 pi j by 5 squared, etc. So powers of that. And that gives you the isomorphism between the groups. Okay, so you get 1 mark for a one-to-one mapping, and 2 marks for getting those elements right. We've got another set here. So this is quite common that you'll get a few different ones and you'll be looking for some sort of similarities and differences. And here we've got x and y are elements of G. It's a group under the binary operation where pairs of elements are combined by multiplying 2 of the elements to get the first one and to get the second one. And they're giving you an example just in case. So 3 times 4 is, so here we've got 3 times 4 is 12, which is 1 modulo 11, and 5 times 4 is 20, which is 9 modulo 11. To write down the identity element, and that should be fairly obvious that the identity element, well, it's going to be the 2 identity elements combined, because that will keep both of them the same, and find an inverse of the element 9, 3. Well, the 3 one's easy because we know 3 times 4 gives me that. Okay, so we know that must be 4 here. And the 9 one, all you need to do is look at the inverse of 9, and you find that's 5. Clear, because 5 times 9 is 45, which is 1 modulo 11. Okay, or you can look back at the table if you've got that handy. So that's just getting you used to using it. Explain why y to the power 5 is 1, 1 for each element. And if you think about the multiplication, so xy times xy is going to give you xx, which is x squared, y squared. So you can see quite simply that that's going to equal x to the power 5, y to the power 5. But we know that G has order 5, so that x to the power 5 is 1, and y to the power 5 is equal to 1. Okay, so that's got to be equal to 1, 1. And deduce that every element of K except for 1 has order 5, state which is the exceptional element. Well, again, the identity element always has order 1. That's the exceptional one. Why have they got order 5? Well, you know that the order of xy, because xy to the power 5 is equal to 1, the order of xy must be a factor of 5. But 5 only has factors of 1 and 5. The identity element has order 1, and that's the only element that can have order 1. So all the other elements must have order 5. Okay, so that proves that fact. And again, looking at that, the comments that I made there, the order of xy is a factor of 5. So you get you 1. Only the identity can have order 1, and 1 to say that hence all the other elements must have order 5. Okay, I think the other ones, it's fairly obvious where you get the marks for in the mark scheme. And so just the last 2 sections of this question. A subgroup of K has order 5 and contains the element 9, 3. List the elements of this subgroup. Well, it obviously has to contain the element 1, 1. We know that. It's got to contain the element 9, 3. And it must contain its inverse. Okay, and we said the inverse of 9, 3 was 5, 4. The best thing probably to do is just look at the element 9, 3. Well, we know that if we combine it with itself, 9, 3 times by 9, 3, let's see what we get. And again, you can look back at your tables for this, or we can just work it out again. 9 9s are 81. 77, so that's going to give us 4 modulo 11. 3 3s are 9, so that's going to give us 9 modulo 11. That's another element. And if we multiply 4 9 by 9 3, doesn't really matter which order because obviously it's abelian. We're going to get 4 9s are 36, which is 3, and 3 9s are 27, which is 5. So I should have curly brackets. So that's our elements. That gives us the 5 elements. There's other things that you can check. You could check, for example, we know these two are the inverses of each other. You could check that these two are the inverses of each other. 4 times 3 gives me 12, which is 1. 9 times 5 gives me 45, which is 1. So we know we've got all the inverses and we've got all the elements. And determine how many subgroups of K there are with order 5. Now, we know that K has 25 elements, okay? Because it says that. It's 25 elements. One of them is 1 1, which leaves 24 left. Now, because they're all cyclic and all the elements have got order 5, that means that if we take an element, any element, it's going to be in a subgroup with 3 other elements, so there's going to be 4 of them together, plus the identity are going to make up a subgroup. Okay, so if we do 24 divided by 4, that gives me 6. And so that means there must be 6 subgroups. Because each one must have order 5, therefore must generate a subgroup of order 5. One of the elements is the identity element, so it'll take 3 other elements with it to make up those 4 ones that make up the subgroup. They must each be in 1, so 24 divided by 4 gives me the 6 subgroups. Okay, and again, if I look at the mark scheme, we've got your marks for getting those 5 elements in the subgroup, and then thinking about how that subgroup works should be fairly straightforward to think, well, take out the identity element, all the other ones must be in. 24 divided by 4 gives me 6. Okay, so that's the end of that question. Just go back to that last slide so you can just see the information about the Further Maths Support Programme. Oops, daisy. Okay, it's gone off again. So if you want to find out any more about the Further Maths Support Programme, you need to go to the Further Maths website, which is shown on this last slide. There will be other recordings for all the other FP3 and also FP2, FP1 sessions. So thank you very much.